Check this out. We've got something really fun today. This is so amazing. Oh man, again? 11.3 The Binomial Theorem. Consider this array of numbers. We start at the top, and each one of these lines represents possible routes we could take. And each number then is how many ways to get to that point. So we start at the top, and this one's 1 because there's one way to do it, and that's because we start here. This one's also 1 because we start here and we progress down this line to get here. Think of gravity pulling us downward. This one is also 1 because there's one line to get here. There's also one way to get here, and that's if we follow this path and then follow this path, like taking two left paths here, and there's just one way to get there. There's two ways to get here. We could take this path and then come back, or we could take this path and come back. And one way to get here because we follow this, and that's the only way to get here. For this third level, then the outside will always be 1. But this one here, there's one way to get to it on this side, and there's two ways here, so then we could drop this way. So you see that we just add the two preceding numbers. So this one, 1 plus 2 is 3, and same with this slot here, 2 plus 1 is also 3. And this one here is just 1, of course. See if you can find the next 3 levels of Pascal's triangle. And hopefully you've got these numbers here. Now let's expand this binomial. So to start off, we would have p plus q 6 times. And then we'd need to multiply all these together and collect up like terms. So pause the video, try this out. Well, that was a lot of fun. We end up with something like this, and I ordered it in descending powers of p, so p to the power of 6 and then p to the power of 5 and so on. There's a few things that we want to notice here. First thing, look at the exponents. They always add up to 6. So 6 and then 5 plus 1 is also 6 and 4 plus 2 is also 6 and so on. And when I write it in descending powers of p, p steps down by 1 each time and q steps up by 1 each time. So q starts from 0 and steps up 1, 2, 3 and until it gets to 6, and p has an exponent of 0 here in the last term. And the final thing we want to notice is the coefficients. Now, how does this correlate to Pascal's triangle? Why would we have looked at that before we did this question? Look at the coefficients: 1, 6, 15, 20, 15, 6, 1. It's symmetrical. And going back to the first slide, we can see that this is level 6 of Pascal's triangle: 1, 6, 15, 20, 15, 6, 1. So we did all that work just to find these numbers that were already here in this triangle. Now, I do label this triangle a bit differently. Lots of people label this one as level 1 and level 2 and so on. But I like to label this first one level 0, so then the level always corresponds to the exponent. The next one would be p plus q to the power of 1, and that would just give us 1 and 1. 1p and 1q. Level 2 is a bit more interesting. It would be p plus q to the power of 2, and we would have 1 p squared. Then we would get 2 pq, and then we would have 1 q squared. And see, p's exponent goes 2, 1, 0. And q's exponents go 0, 1, and 2, and the coefficients match this row on Pascal's triangle 1, 2, 1. Let's try that by expanding this binomial. So we would be looking at row or level 4 of Pascal's triangle. So the exponents on level 4 are 1, 4, 6, 4, 1. So this would be 1, and then 4, 6, 4, 1. Now, first x gets all the exponents, so it's x to the power of 4. The next one, x to the power of 3, and it counts down until x to the power of 0 is the last term. Next, we want y to the power of 0 here, and then y to the power of 1, y squared, y cubed, and y to the power of 4. And we probably don't want to write a coefficient of 1, it's a bit unnecessary, but the rest of this looks good, and we don't have to collect up any terms either, it's already done for us. So this was a lot easier than multiplying out the binomial to the power of 6, and a lot of students will ask me, well, why did you even make us do that? And it's simple, so you could appreciate this binomial theorem. Okay, now this is great, level 4, but what if we wanted to expand out this binomial to the power of 11? We'd have to draw Pascal's triangle down to the 11th level, which is possible, but it wouldn't be fun, and you might make a mistake. So there is another way to get the terms in Pascal's triangle, and that's to use combinations. So we can think of how many movements we've made and how many movements were to the right. Conversely, you could also say to the left and reverse this. It's all symmetrical, so it doesn't matter. But here we have made 0 movements, and 0 of them have been to the right. Here we made 1 movement, and 0 of them are to the right. And 1 choose 0 is just 1, and 1 choose 1 is also just 1. So all of these combinations give us the values in Pascal's triangle. See if you can write the rest of these values of Pascal's triangle in terms of combinations. So it should look like that. So going back to the example that we did the long way, p plus q to the power of 6, we can use combinations to find the coefficients instead of going through all that work. So this would be 6 and 0, 6, 1, 6, 2, and so on until you get to the last one, 6, 6. Just remember that you start off with a choose 0 here. And then for p's, count those exponents down, and for q's, count the exponents up, and we get the exact same answer we did before, except with a lot less work. So this works for any binomial expansion, x plus y to the power of n. So the n would just go here, it would start with 0, as I said, and x at first gets all the exponents, and y gets none of them. And then it gradually works its way up till we have the reverse. Now there is a formula for the individual terms that's given on our Math 30-1 formula sheet. So it looks like this. So term k plus 1 is equal to n choose k, x to the power of n minus k, y to the power of k. And this will find you individual terms if that's what the question is asking for. Like this question that wants us to find the second term in the expansion of 3a minus b to the power of 5. Now we've got some numbers mixed in here and a negative sign. Just make sure that you keep the negative with the b. So our exponent here is 5. So when we're doing the second term, we would like to start with 5, choose 1. Remember the second term is 1 here. The first term is 0. Next, I'm going to use some brackets just to separate it to make it clear, but this is our first term here in the binomial 3a. And for the second term, you can use the formula if you like, but the second term is pretty easy to remember how to do it. The first term would be all 5 given to this guy, and the second term, he would just have 4. This one here, negative b, is our second term. And that would have an exponent of 1. Remember, these always have to add up to our exponent of 5. Now we can clean this up a bit. 5 choose 1 is just 5. 3 to the power of 4 is 81. And a to the power of 4 is just that. And negative b. I'm going to put the negative and all the numbers together at the front here. So negative 405 a to the power of 4 times b. And that would be the second term in the expansion of this. How many terms exist in the expansion of 2a minus 7 to the power of 8? So there's 9 terms, and remember, always one more than the exponent. What is the fourth term in the expansion of 2a minus 7 to the power of 8? So the fourth term here would be 8 choose, and then we're doing the fourth term, so it'd be 3 here. And then look at the first term, 2a, and it's going to have 5 as its exponent, and negative 7 is going to have 3. Now, when we calculate this out, we get that this is 56, this is 32a to the power of 5, and this is negative 343. When we collect up all the numbers here, we get negative 614,656 a to the power of 5. Now, if you need a little bit of help on the first step here, then you can use the formula that we have on our formula sheet. So it looks like this. T k plus 1 is equal to n, choose k, x to the n minus k, y to the power of k. So we need to figure out what k is. We want the term to be 4, so 4 equals k plus 1. That means that k is equal to 3. And the n here is the exponent, so n is equal to 8. So for this one, term 4 is equal to 8 choose 3. There's the n value and there's the k value. And then x is the first term in our binomial, so it's 2a. And then this would be 8 minus 3. And the y here would be the second term in our binomial, negative 7 to the power of 3. Now, when you simplify this, it's going to look exactly like this, and so we'd still get the same answer. But this gives you a little bit more structure and helps you remember what to do. In the expansion of a squared plus 1 over a to the power of 5, which term in simplified form contains a single a? Determine the value of the term. Now we could just try out all the terms until we find the one that just has an a. So term 1 here would be 5 choose 0, and then a squared to the power of 5. That's going to give us an a to the power of 10, so that's not what we want. Let's look at term 2. 5 choose 1, a squared to the power of 4, and 1 over a to the power of 1. Now, this is going to give us 5 choose 1, and when we collect up these a's, we got a to the power of 8 minus 1, so a to the power of 7. So that's, again, not what we're looking for. Term 3, 5 choose 2, a squared to the power of 3, and 1 over a to the power of 2. So this would be 5 choose 2, a to the power of 6 minus 2, a to the power of 4. So this is also not what we want. T to the power of 4, 5 choose 3, a squared to the power of 2, 1 over a to the power of 3. Now this is going to give us what we want. We got a to the power of 4 and a to the power of 3 in the denominator, so that simplifies to a single a. So this is the term we want. Now this might take a long time, especially if the term we want is very far down the line. We'd have to be trying all of these terms. So let's see if we can use our formula. T k plus 1 equals n c k x to the power of n minus k, y to the power of k. Now, I don't really care about the coefficients, so I'm just going to leave a box here, and it's just some coefficient here. I don't care. And I want the a's though just to be a single a. Same with this. I'm just going to leave this blank. I'm not going to care about it. Some coefficient. Now, this one here is my a squared term. And this part right here is remember the n is the exponent, so it's 5 minus k. And my y is my second term, so 1 over a, and this will be to the exponent of k. And now I can just solve this. The only thing I don't know is k. So on this side I've got a, on this side I've got a to the power of 10 minus 2k. On this side I'm going to get this a out of the denominator and give it a negative exponent to do that. Now I can put those two numbers together. So a, then I got 10 minus 2k minus another k. And now that my bases are the same, I can drop the base. So 1 is equal to 10 minus 3k, plus 3k on both sides, minus 1 on both sides. I get 3k is equal to 9, divide by 3 on both sides, I get k is equal to 3. Don't get confused, that's not the term number. Remember, the term number is k plus 1. So term number 3 plus 1 is equal to 4. So either way, we would find out that the term number is 4. Using the formula to finish off using this method, though, we'd have term 4 is equal to 5, choose 3, a squared to the power of 2, 1 over a to the power of 3. And we kind of already know this one's going to just simplify into a based on what we were trying to do. And 5 choose 3 is 10. So term 4 is 10a. This was part of Binomial Theorem 4. Expand powers of a binomial in a variety of ways, including using the binomial theorem. And we're restricted to exponents that are natural numbers. Here's some questions. Give them a try. See if you know what you're doing.